the standard normal distribution. So the standard normal distribution is just a continuation of normal distribution. So the first thing we're going to do is just write down our probability density function for the normal distribution. So for a normal distribution, our probability density function is 1 over the standard deviation times root of 2 pi times e to the minus a half of x minus our mean over our standard deviation all squared. So our definition for a standard normal distribution is that we're going to have a mean of 0 and a variance of 1, which just means we're also going to have a standard deviation of 1 if we square root both sides. So let's go ahead and plug those values in. So it's for our standard normal distribution. We're going to have 1 over 1 times root 2 pi is just going to be 1 over root 2 pi. E to the minus a half of x minus 0 is just x. So we're just going to have x squared over 1 squared, which is just 1. So we end up getting this for our definition for the probability density function for a standard normal distribution. And what this does is, if we remember from our normal distribution, we had a bell curve that was centered around the value of our mean. But now if we make that mean equal to 0, we end up getting our standard normal distribution centered around the y-axis because our mean is now equal to 0. And since it's going to be symmetrical about this y-axis, we can use some properties here. But before we talk about properties, let's just talk about some notation. So a standard normal distribution, we actually note it with a z, and it's a normal distribution which describes the mean as 0 and the variance of 1. So this is what defines our standard normal distribution. So also if x is going to equal the normal distribution with some mean and variance, then we can actually calculate a value z that will equal a given score minus the mean over the standard deviation, which standardizes our normal distribution for scores of z, which might look something like this. So a score of z could be here, and it could be, we're going to use the fact that we're symmetrical, and we could have a score of minus z over here. And what would occur is that any area that was greater than z would actually equal the area that was less than minus z. So the way we can write that is we can say that if we wanted the probability that a score was less than minus z, which is all of this area here, we can say that also equals the probability that a score is greater than z, which is this area here. This will also equal 1 minus the probability that a score is less than z. So let's have a look at what that means. So 1 represents the area of the whole thing. The probability that the score is less than z is all of this. So all of this minus this also leaves us with this part here. We can also write another expression that said it also equals 1 minus the probability that a score is greater than minus z. So a score that's greater than minus z would be all of this. 1 representing the whole thing. So 1 minus this part also leaves us with this part. So all 4 of those expressions are equal. Which also gives us the fact that if we just look at this part here of the equation and minus 1 from both sides and divide by the negative left over, we also get the fact that the probability of a score that's less than Z will equal the probability of a score that's greater than minus Z. Now, by having a standard normal distribution, we get the same special results that we had for normal distribution in terms of the percentages, but they're all just centered around the y-axis. So for a score of Z equals 1 and score of Z equals minus 1, this encloses 68% of all scores. For Z scores in between 2 and minus 2, this encloses 95% of all scores. And finally, for scores of Z equals 3 and minus 3, so including all of these as well, this encloses 99.7% of all scores. So let's have a look at some examples. So if we set a maths exam and an English exam, and the maths exam could be represented with a normal distribution of, let's call it X, and a normal distribution defined with a mean of 30 and a variance of 9, and the English exam with a normal distribution of mean 80 and variance 25. In the maths exam, let's say we got a score equal to 36, and in the English exam, a score of 88. And we want to know which test did we do better in? Which test did we do better in? Now, here we can use the standard normal distribution to figure out which test we went better in relation to the mean and standard deviation. And we can do this with Z scores. So by changing our data to a standard normal distribution, we can do that using a formula to calculate a Z score that equals the score that you received or the score that you're interested in analyzing minus the mean over the standard deviation. So for the maths exam, our variance was 9, which means our standard deviation is the square root of 9, which is 3. And the English exam, the standard deviation is the square root of 25, which is just equal to 5. So let's go ahead and find the Z scores for both exams. So for the maths exam, the Z score will equal the score that we received, 36, minus the mean, which is 30, over the standard deviation, which is 3. So we get 36 minus 30, which is 6, 6 over 3, which is 2. So we get a Z score of 2 for the maths exam. For English, find our z-score. That'll be the score we received, which was 88, minus the mean, which was 80, over the standard deviation, which was 5. So we get 88 minus 80, which is 8 over 5, which is 1.6 for the z-score. And now we can see that the z-score for the maths exam was higher, which means we performed better in the maths exam, as the z-score is higher. Let's look at one more example. So for a normal distribution, if we have the probability that a score is less than A is 0.254, and the probability that a score is less than B is 0.467, and we know A is less than B. First thing we want to do is find the probability that a score is greater than A. So in order to do this, it might be best if we draw a little diagram. So let's go ahead and draw a probability density function. And let's draw it as a normal distribution, because it did say in the question that it's a normal distribution. So we should note that down. This is a normal distribution. And we'll make it a standard normal distribution. And let's go ahead and mark in A and B. And we know A is less than B. So we could mark in A here and B in here. And we know the probability that a score is less than A is 0.254, which means that everything from here, all this area here, is 0.254. And we know that the area, well, the probability of a score being less than B is 0.467. So we know all of this is 0.467. So what's the probability that a score is greater than A? Well, we know everything on this side is 0.254. And we know the total area is equal to 1. So the answer is just going to be 1 minus 0.254, which is going to give us 0.746. Another question, what is the probability that a score will be greater than B? Well, again, we know everything that's less than B is 0.467. We know everything on this side needs to make it add up to 1. So that just means the answer is going to be 1 minus 0.467, which is going to give us 0.533. And finally, what's the probability that a score will be between A and B? Well, that's just the area of this part in here. We know all of this is 0.467 and all of this is 0.254. So subtracting those two areas will give us the area in between. So we're just going to get 0.467 minus 0.254, which is going to give us 0.213 for our probability.